So, yes, the title is What Can We Learn About Dark Energy in the Next 10 Years? I was asked to focus on the future and the next potential breakthroughs. Chuck mentioned a number of tensions that are starting to creep into the standard model of cosmology, the so-called lambda CDM model. I'm just going to talk about lambda in lambda CDM a little bit, and the real question is lambda the right answer for what that first term in the current standard model is? So this graphic is probably famous, probably well known to many of you. This is a schematic timeline of the evolution of the universe from the Big Bang, or actually the inflationary epoch in the very far left here. Time is running to the right, and the relative size of the universe is the vertical scale. So we have this initial exponential growth in the scale of the universe called cosmic inflation that we're trying to pin down and get better evidence to see if that event actually happened. I'm not going to talk about that today. The microwave background radiation on the kind of blue-green screen on the far left is the background radiation that WMAP measured, and that was the baby picture of the universe, the farthest away we can see in the universe with photons, with light. That told us a tremendous amount about the composition, the age, and the shape of the universe. And then the universe has evolved. It's grown by a factor of 1,000 since the background radiation was emitted. And the expansion, for many years, we thought the expansion was slowing down as the gravitational mass of stuff in the universe caused the initial expansion to slow down. But with the supernova results in late 1990s, it became clear that the universe was actually starting to speed up again. The expansion was accelerating, and that idea was really cemented with the WMAP results and other microwave background measurements in early 2000s. So that there's really no doubt now that at late times, over the last half of the age of the universe roughly, the expansion has been accelerating. And we attribute that to what we call dark energy, and the best model for dark energy right now is this cosmological constant lambda. But we really have no clue as to how lambda fits into fundamental physics now. It's quite at odds with our ideas of quantum field theory and what we know about the standard model of particle physics. So it really is one of the great challenges going forward in astroparticle physics, cosmology, and fundamental physics. And I'm just going to talk about a project we're doing up in Canada to try to get a better measurement of dark energy. And that's, let's see, I guess I got the right button here. That leads me to the subtitle of my talk, Listening to the Universe with CHIME. CHIME is another acronym like MAP. I'll tell you what it means in a moment. But it's a novel new telescope for cosmology that I will talk about more shortly. This is a nighttime shot. I guess you can't really see the night sky very clearly in this view, but this is a very goofy-looking telescope, and I'm going to tell you why we built CHIME and why it looks so funny. The most important, I think, nugget to take away from the microwave background observations is the fact that the map itself looks like random noise. It's just got hot and cold spots all over the sky. And it's really hard to imagine that contains so much incredible information. The key to this information is what we call the acoustic fluctuations, the Baryon acoustic oscillation. And simply put, if you just take every hotspot in the map, and there's about 11,000 isolated hotspots, and you just look at the average profile, you just take them all, average them together, and stack them, the average hotspot looks like the picture on the left there, where it's got a hot spot in the middle, of course, because that's what you selected, but it has a cold ring around it that is not at all what you expected, or not at all to be expected just statistically. And that's an acoustic wave that was set in motion at the end of inflation, propagated for 379,000 years at the speed of sound, and then froze in place when the plasma became neutral and the microwave background was released. So the profile of that shape contains an incredible amount of information about the dark matter, and the properties of the plasma that this sound wave propagated in. And that's really the key to the power of the microwave background radiation. And the main point for today is that feature, that acoustic shell, is also preserved in the large-scale structure we see today in galaxies. So if we do a survey of the nearby universe, just look at galaxies, make a map, a three-dimensional map of galaxies. If we know how to look for the pattern in this three-dimensional map, we can see the same acoustic feature in the galaxy distribution today. And we know how big that is. Chuck mentioned this as a standard ruler. And so this gives us something that we can measure distance with in cosmology. And measuring distance in astronomy is one of the hardest things in the world to do because you just have no reference frame for how far away something is. So if we can map the nearby universe, the galaxy distribution on large scales, and see this BAO feature, the BAO scale, or the acoustic fluctuation, we can tell how far away these objects are that we're looking at. And from that, we can measure the expansion history, the rate at which the universe is expanding at late times, and get a better handle on whether dark energy is a cosmological constant or maybe something else. So that's the goal, the name of the game we're after, is to map the nearby universe, to map out this feature. What we need to really map this precisely is statistics, or volume. So just like the microwave background, we had to map the entire sky to average enough hot spots together to see this feature clearly. With the galaxy distribution, we need to do the same thing. So we have any individual hotspot has a ring around it, but it's completely confused by all the other hotspots nearby. So if you look on the left, you can see the same pattern on the right is present in the left, but it's a bunch harder to tell, right? So what you need to do is just get an enormous volume and average lots of overdensities together to be able to see this feature clearly. So we need to make a large map of the volume, of the nearby volume, to make a useful measurement for dark energy science. So traditionally this has been done, and it has been done for quite some time now, with galaxy surveys. So you take an optical telescope with high angular resolution, you measure the position and the spectrum of a galaxy, of an individual galaxy, and put that as a point on your redshift survey, if you like. And then you analyze the whole point set to look for this BAO feature. And the point I want to make here is that the BAO feature is enormous. It's 150 megaparsecs, which is 450 million light years in layman's units. None of us can really imagine how large that is. But it's much larger than the scale of a galaxy. So you don't need to measure individual galaxies to see this acoustic feature. If you had a way of just measuring the universe at low angular resolution or low spatial resolution, you still have enough information to extract this acoustic feature, and you can do the distance redshift relation that you want to get the expansion history. So we have a technique that we're employing in Canada called hydrogen intensity mapping, which is, I'll describe shortly. And we have a special purpose telescope called CHIME, or the Canadian Hydrogen Intensity Mapping Experiment. Like MAP, CHIME is intended to be a clever acronym using this sound, inspired by the idea of sound. And we have just finished construction of CHIME. We had a first light ceremony in September, and I'll describe a little bit about the concept. But this is a photograph of CHIME. It's I think I can go backwards here. It's situated in the interior, the Okanagan Valley of British Columbia, a beautiful tourist destination for many Canadians in the summer. But it's also a site of a National Radio Astronomy Observatory in Canada. It's got a radio-protected valley that shields us from cell phones and all kinds of sources of radio frequency interference. So this is CHIME on the site of the Dominion Astrophysical Observatory. For scale, there's 4 cylinders here. Each of the stairways leading up to the cylinders is a 2-story stairway, and the 3 of us who are taking this drone video are standing at the bottom of the far stairway. So this is a large steel structure, quite impressive actually, and it's in a beautiful high desert valley in the Okanagan Valley. I will say, I'd like to point out that the principal investigator of CHIME is my colleague Mark Halpern at UBC. He was also a WMAP colleague and a breakthrough recipient last night, so just shout out to Mark. some vital statistics of the telescope. CHIME is it's a drift scan telescope, so it has no moving parts. It just is 4 cylinders that are static steel structures. Each one is 20 meters across, 100 meters long, so it's an 80 meter by 100 meter footprint, so a rather enormous collecting area. The field of view, the reason for I'll go into this in a little bit more detail, but the reason for this cylindrical shape is that we're trying to get an enormous field of view, an instantaneous view of the sky at any single time, and this kind of design helps us do that. We cover half the sky. We're going to try to map half the sky visible from Canada, and we do that every day with this enormous field of view. I'll describe a little bit about that. The frequency range we operate in is in the radio frequency range. It's 400 to 800 megahertz, which, and what I should say that the point of the measurement is to map neutral hydrogen gas. We're using the 21 centimeter emission line, which is the most abundant radio emission line that neutral hydrogen puts out. And then we're looking at that in a redshifted spectrum frequency range. So 400 to 800 megahertz corresponds to looking at an epoch in cosmological history when the universe was roughly a third to a half of its present day age, or a redshift of roughly 1 to 2 in the vernacular. And so CHIME is a radio telescope that operates over this entire octave of waveband, 400 to 800 megahertz, to measure this redshifted 21 centimeter line to map the distribution of neutral hydrogen on large scales, which traces the distribution of galaxies on large scales. Is there anything? Yeah. So just a couple of slides about how CHIME works conceptually. We have these cylindrical telescopes. If we place a single receiver at the focus of a parabola, the cross-section of the cylinder, the radiation from that will be focused onto the sky, and that receiver will be sensitive to an enormous swath of the sky overhead, roughly about 2 degrees across in the east-west direction and 120 degrees in the north-south direction. And so that's what gives CHIME its enormous instantaneous field of view. But a single receiver has almost no spatial resolution. You can't tell where in that blue swath that the radiation came from, so it's a useless receiver for mapping the sky. To actually get spatial information or localization information, you need to have a whole bunch of receivers. If you take a pair of them, then this pair of receivers is sensitive to a sequence of hot and cold spots along the north-south direction. And you can use that combination of information to start to localize where the radiation is coming from. If you fill the entire focal line with receivers, with a Nyquist sampling, if you like, then you can start to then reconstruct the north-south position information, and you can localize where radiation is coming from by combining the information from all these receivers simultaneously to see where in the north-south direction it came from. And finally, if you have 4 cylinders and you put them all together, you can also do the same kind of thing by combining the cylinder information in the east-west direction. And you can simultaneously basically reconstruct beams, if you will, on the sky that completely fill this field of view. And so you can think, and then the sky rotates overhead once a day, and so this entire sweep of beams just fans across the sky every day and measures and maps the sky. So that's what gives it the enormous mapping speed that is required to get a large volume survey of the universe. And so this just schematically, the red slash there indicates kind of roughly the field of view of a single receiver. This is in a coordinate system where the celestial equator of the Earth is across the middle of the band, the north celestial pole is at the top, and you can see how the galaxy arcs across the sky in this rendition. But it's basically mapping the entire northern half of the sky every day. And then we just need to repeat that measurement to build up enough sensitivity to see this faint BAO signal. So CHIME, as I mentioned, it's now operating. We had first light in September. And this is a big data experiment. We have 2,000 such receivers on our 4 cylinders. So the basic information that lets you reconstruct all of these beams is the correlation matrix between all the pairs of receivers. We can represent that correlation matrix as a big 2,000 by 2,000 matrix of data from which we then extract these individual pointing information. We collect one of these matrices every 10 seconds, and we have, says 10,000 such samples per day, and we have 1,000 frequency bands. So this 2,000 by 2,000 matrix represents 1/10,000,000th of our data per day. And this is already highly compressed from our raw data rate, which is about 13 terabytes per second. So it's very much a big data challenge. We now currently have the fastest back-end correlator computer on CHIME that's been working. And we have a tremendous path ahead to try and actually make sense of all this data, but it's going to be a very fun challenge to try and come to terms with. At the end of the day, if all is successful, the kind of distance measurement sensitivity we can get by taking this, measuring the angular size of the BAO scale and seeing how far away that scale is gives us a distance measurement at each redshift or each epoch of cosmological history. We think that we'll get to a bit under 1% per bin in redshift space, and from that we can reconstruct the expansion history. And with any luck, we can either determine that the expansion rate, that the dark energy is not consistent with the cosmological constant, or more likely that it is. There's really no compelling model in the parameter space of dark energy that is anything else other than a cosmological constant. But if we do find something significantly different, then that points us in a completely new direction for future studies. So that's it's a potential breakthrough in the next 10 years that we hope to be a part of. Thank you.
Super, very exciting. Okay, we have some time for questions. It's hard to see with the light sometimes. Yeah. Right here, Leonardo.
Hi, what are your perspective for increasing the resolution of these kind of experiments so that we can do with them not just dark energy, but also continue to do inflation and the beginning of the universe?
So I think I missed the beginning of the question.
What are your perspective for increasing the resolution of this kind of
spatial
resolution so that you can get much more modes?
Yeah, it's so telescopes like ALMA are now operating with a more sparsely sampled array, so dishes that are spread out over the Atacama Plateau, for example, and so the angular resolution is really set by the spacing of the largest spacing of any pair of receivers you have. So there's definitely opportunities for doing different kinds of array geometry with this kind of technique that has great promise, I think. And things like the square kilometer array are looking in that direction for the future. I think one of the big challenges that I completely glossed over here is the foreground emission, that we have to, this 21 centimeter signal we're looking for from the galaxies out there is is very faint compared to the radio emission from our own galaxy. We have to be able to filter that out, and we need to demonstrate that we can actually do that still. So that until I really am confident that we know how to do that, I'm hesitant to invest vast sums of money on something more ambitious. I should say that CHIME is a fairly quick and dirty kind of approach to this kind of problem. So.
One question over here.
Thank you.
I have to do coronagraphy here with my hand to see. Sorry.
Is there any chance of using scanning array technology for achieving a larger aperture area? Are the signals coherent in time enough to allow that?
Well, let's see. How large are you thinking?
Well, for instance, the motion of the Earth gives you your scan,
You're right, the rotation of the Earth, right?
Yes, or its revolution as well. But I guess it depends on how time coherent the signals are as to whether you would be able to use the scanned.
Right. Well, we're just assuming
advantage.
coherence across the light crossing time of our array, right? So that's, and as long as the signal's coherent between all pairs of receivers, then we can extract that, right? So that's the time scale on which you really have to have confidence, right? So.
Actually, may I ask, because somebody's foreground is somebody else's signal.
Yeah,
What are the things you hope to learn actually about the galaxy from this pathfinder?
Well, there's so one of the things there's a tremendous amount of information about the interstellar medium, which is the brightest foreground comes from synchrotron emission, which is due to cosmic ray electrons spiraling around the galaxy. This is highly polarized, and there's a technique called rotation measure synthesis, which is kind of Fourier transforming the signal in the frequency direction to extract three-dimensional information about the galactic structure. So that's quite an interesting project for the future for doing 3D mapping that really has heretofore not been possible.
And it's sensitive to the three-dimensional magnetic field structure as well?
At least a projection of the three-dimensional projected field, yes,
Exactly,
that's right.
yeah. Very good. We would have time for one quick question. Well, very good. Let's thank Gary again.